All right, so let's get started here with this unit. So this unit is a lot of information that you've seen before, Danny. Shh. But it's going to be taking it at a new kind of level. So you've seen kinematics, you've seen dynamics. We're going to change this now and apply it to circles. So what's going to happen if you apply these things to a circle? And we are going to be dealing with uniform circular motion. So what that means is that, so uniform obviously means something is constant. And in this case, we've got a constant speed. Nope. Constant speed, not velocity, because your velocity is not going to stay the same. Well, you'll find out. So, in order to do this, we're going to derive an equation here to get you the basics into what we're dealing with. So if I were to give you the equation for speed, this is just going to be distance over time, because it's uniform, we're not accelerating. So this is our equation for speed. So if in a circle, well not if, because it's always defined as this, in a circle if you do one full rotation, this is known as the period of motion. So the time it takes to do a complete circle is the period, and we need to figure out how far does it travel in a rotation. So if I'm looking at my circle here, suppose I've got my object, whatever it is, it's going around the circle, it keeps going around. What distance does it travel total? One circumference. So what's my circumference? What's the equation for that? So the distance traveled is 2 pi r. This is just your circumference. I filled that in. We can find it by this. Could go here. How far does it rotate? It's just one circumference. So therefore, specifically for circles, we have this equation for the speed. Speed equals distance, which we just said is 2 pi r, according to a circle, divided by the time it takes to do that complete circle, which is the period. So capital T, this is period. Like a few other variables, I don't know why they picked T. Probably because you've got power, you've got momentum, other things that look like a P. Could be time. Capital time for this is a very special time. So this is the speed equation for a circle. Again, we say speed because as you move around a circle, your velocity is going to change. And I'll show you that in a sec here. Speed, easy. Is the mass accelerating? Well, what's our equation for acceleration? A equals change in velocity over time. If you want to be technical, we can put the vector arrows. It doesn't really matter. So does my velocity change? The magnitude of my velocity does not change because the speed is constant. However, my velocity does change. It just changed direction. It doesn't change its magnitude, it changes its direction. So if I'm here, suppose I'm going around clockwise, my velocity is in this direction. If I'm on this side of the circle, now it's down. I'm here to the left. If here, it's moving up. Pardon me? Yep, your velocity is always tangent to the circle. So this is all your velocities. Your velocities change direction. And because your velocities change direction, you must have an acceleration. So as Hashem said, notice the direction is always going to be tangent to the circle. Yep. Circle. So anytime you have something moving in a circle, you have acceleration. So you're going to have something that's changing. What direction is the acceleration? Clockwise? No.
Well, like, then you say that.
No, like in the velocity is either going to be clockwise or counterclockwise depending on the rotation. No, not counterclockwise. No. Your acceleration for a circle, always towards the center. I didn't expect you to know this. Just seeing if you could guess it. Acceleration is always pointing towards the center. Your object is always trying to get towards the center, but it has some sideways velocity, so it's rotating around. Think about gravity. The moon's orbiting around the Earth. It's got some velocity going around the edge of its orbit, but it's trying to accelerate towards the Earth. It's just because it has a horizontal or perpendicular component that causes it to rotate. So, let's summarize this. So even though it may be traveling at a constant speed, anything traveling in a circle must be accelerating because your direction of the velocity is changing. Direct. So this acceleration, we've got two equations for this. I'm not going to go into the derivation of it, but the centripetal acceleration, I'll explain centripetal in a sec. The acceleration that we have going towards the center here is equal to the speed squared over the radius. And if we plug in, again, there's a derivation for this. If we plug in the equation we had up above for the speed into this, we can get a second equation of 4 pi squared r over the period squared. Again, you don't need to know the derivation of it. You just need to know that there is this equation. Nope. The r is not negative in this case.
Why is the r not squared?
Again, well, because when you square it up here, you're going to divide by r here. Yeah, you can plug it in, you'll find out. So again, I'm not going to show you the derivation. That's not important at this point. It's worth noting from this derivation, so our change in velocity is always towards the center of the circle. So therefore, the acceleration must always be towards the center. He's always towards the... So this acceleration is called centripetal, just down here. So centripetal means center seeking. That's just the definition of centripetal. So if you have a centripetal force, it's seeking the center. Yep.
Is that like where kind of force of gravity or like gravitational force comes from? Like the Earth's gravitational force?
It comes from gravity, but we can apply it to a specific situation if we're going to travel a circle around the Earth.
So like maybe like it's going, like its the acceleration is towards the center.
Mm-hmm.
So like how it's hoping to move within its like force of gravitational
Yeah.
force.
Yep, which will be the next section. Yes, so that's why this is going to be very similar because force of gravity is a center-seeking force. If I have an object attached to a rope and I spin it in a circle, tension is now my center-seeking force. So this is why it's very similar to what you've seen before because you've seen some of these. So whenever we have an object accelerating, we must have a net force. You can see how this unit combines a whole lot of things. We've got dynamics with net force. We've got some kinematics with some velocity in there over time. We're going to have some gravitation, which is kind of already dynamics. Nope, momentum is not going to be in this, but we'll get into energy. So we got a lot of things going into this. So as we said, centripetal force. So in this case, the centripetal force is the net force. So the definition of centripetal, yes, it's center seeking, but the centripetal force is just going to be the net force specific towards circles. So anytime I use the word centripetal force, you can imagine or replace that with net force towards the center of its circular path, so towards the center of the circle. Centripetal force is just a net force. So we're going to get some F-net equations going on here. So if I have a mass twirled in a circle at the end of the string, what is my centripetal force? Tension. Tension is what's causing our object to go towards the center. Yep. Yes, there will be two capital T's. This is why scientists started using Greek letters, because there's lots of letters that are used. When a car rounds a corner on the highway, what's going to be its centripetal force? Which is also known as friction. Friction between the tires and the road. Yeah. If there's no friction on the road, you can't turn. You also can't stop. If I've got the moon orbiting the Earth, what is it this time? Gravity. So lots of stuff that we've taken in the past is going to pop up here. So applying Newton's second law to this, we can get another formula for centripetal force, or we can get the equation for centripetal force. So force, I'm going to put C for centripetal. Do you remember what Newton's second law is? That's the third, MA in this case. So if I'm looking at centripetal force, I'm looking at centripetal acceleration. Yeah. And because we already have some equations for the centripetal acceleration, we can create two equations. mv squared over r, because v squared over r is our centripetal acceleration equation. And sorry, I forgot the m here. Doesn't matter the order. M 4 pi squared r over capital T squared. So here is our main equation. That's going to help us solve some equations. Everyone got that written out? Now let's actually do examples. We've done a lot of concepts to get us started here, but let's do some examples. So calculate the centripetal force acting on an object when it is twirling in a circle at a speed of 2.3 meters per second with a radius of 0.6. So we want, what is it saying? We want force centripetal. And based on the information we're given, which part of the equation am I going to use? mv squared over r. I have the mass, I've got the speed, I've got the radius. So this one's pretty straightforward. The radius needs to be in meters? Yes, the radius always has to be in meters, just like speed is meters per second, so on. So if you thought it was confusing in last year when we did dynamics and you had to take your gravitational acceleration and divide by r squared, now I'm going to mess with you even more. Now you're just dividing by r. So you can imagine once you get to your test, you need to be very careful when you square the r and when you don't.
Are there radians?
Are there what? Radians? No, we're not going to deal with radians. And we're not going to deal with angles in this. Others, that was a lie. We do with angles when we have banked curves. We'll get to that.
What? Triangles? What's the difference?
You'll find out. A curve that's banked.
There are no radians in physics. Well,
No, we don't deal with radians. So plug this in your calculator. What do we got? Do I have the same question? I definitely do not. Same numbers though, right? 13.225. That would make sense. But my numbers are different on my page.
it's going to be.
Yeah. Let's just go 13.2 and force, so newtons. Not too bad. That one's pretty straightforward. So now we got a car going around an unbanked curve. Unbanked means it is not at an angle. And we have a radius. We want what's the centripetal acceleration. So based on what we're given in the question, which equation are we going to use? Good. Since that's what you're given, we have the speed, 14 squared over 96. This one I know I have written down, 2.04. And meters per second.
This was speed of flow.
Speed, always speed. Yeah, we're not going to deal with velocities with this. It's always, centripetal acceleration is always towards the center. So you don't need to give direction for this because it's given that it's towards the center. So now we want to know what's the minimum coefficient of friction between the road and the car tires. So if we were to look at this car's circle, essentially what we've got is this. So here's our circular path. Here's our car. We're doing a kind of 3D model. So like always on the car, we've got FG, we've got FN, and we've got some F friction that's pulling towards the center. And as always, well, not always, as it is usually the case, Fn equals Fg. So if you remember, I said that your centripetal acceleration is your F net towards the center of the circle. So my net force is just simply force of friction. And this is equal to force centripetal, because it's my net force. Yeah? Why is there no what? Because it's accelerating this way. Actually, no, it's moving at a constant speed around the edge. So there's no acceleration around the circle, just an acceleration towards the center. That's just the given and what we assumed at the very beginning of this unit.
So if a friction is the thing that's causing acceleration?
Yes. And it's not accelerating faster around the circle. It has a constant speed. It's just its direction changes towards the center. So given this, we can now figure this out. So we know force of friction, because these two are balanced, is mu mg. Force centripetal, this one is mac. Conveniently, the masses cancel, because we're not given the masses. So to solve for mu, it's AC, which we just figured out, over 9.8. 0.21. Yes. Yep. So your definition is FC is always your F net towards the center of the circle. It's always going to be the case. Questions with that? All right.
So that C is equal to F has to also be equal to
Yeah. Yeah. Okay. So we've got a plane who's doing a circle. So again, we can draw what our plane's doing. Here's our plane. Do it as a box because everything's a box. We're told what the radius of the circle is. We're told the period, the time that it takes to go around. We want to know the speed. So in this case, speed is, yeah, good. So we're going to use this equation, 2 pi r over the period. So 2 times pi times the radius, we're told, 3,622. Over the time needs to be in seconds. So this is 2 times 60. Oh yeah, just 2.1 times 60. What does that give you? 100? Yeah. Plug it in, 180. Again, speed, so we don't need direction. Questions with that?
You're saying it's speed centers over velocity.
Yeah, but it would just be your direction is tangent to the circle. Okay, one last note on something that we're sort of dealing with, but not really. So there's something that's called the centrifugal force, just to mess with you. We've got centripetal and we've got centrifugal. These are two different kinds. Centripetal means what? Center seeking. So centrifugal means center fleeing. So centrifugal is non-existent. It's a non-existent force. Well, why would they call it a specific name if this force doesn't actually exist? Because you feel something like this. So if you're driving in your car, you're driving like this, and you slam to the left like this, where does your body go? The opposite way. So it feels like there's something that's pulling you away from the center of the circle. This. So Newton's first law, the first law tells us an object in motion wants to stay in motion. This motion is in a straight line forwards. Yeah. So if you're driving your car like this and your car turns this way, you want to keep going straight. Inertia. So when the car turns, it feels like you're slamming against the outside because your body wants to keep going straight. So this centrifugal force, the force that seems to be pulling you to the outside, is really just your inertia wanting you to go in a straight line. And whatever object you're in is pulling to the left or right, whatever way. So what do I need to write in this? Inertia. Nope, we cannot have a formula for a force that doesn't exist. So this is just inertia force. No, not that I've heard of. I've never had to measure centrifugal force.
Isn't inertia that if you're driving straight, your car going just straight and then your body's going to the back?
That's if you were at rest and your car's accelerating forwards. Then you would feel an acceleration backwards.
But there's no acceleration and moving in the same direction.
Yeah. Yeah, so if you're traveling at a constant velocity going straight, you and the car have the same inertia. Well, you don't have the same inertia, but you have both inertia going forwards. As soon as your car turns to the side, your body wants to stay with that same inertia.
Like you turn that, so your body wants to go like down.
Yeah, I already explained that.
So like acceleration, with that, when you accelerate,
Yeah, so there's different cases. If you slam on the brakes, your body's inertia wants to go forward, the car wants to stop. Or when you step on the acceleration, the car wants to move forward, but your body wants to stay at the same space. Yeah, it's just important to know. You're not going to be tested on this, but just an important kind of force. Because it seems like there's something that pulls an object to the side, but there isn't actually anything pulling you. Yeah.
it's not something directly related, but it's inertia, basically the transfer of energy.
Inertia is not a transfer of energy. It's kind of like your body's momentum in moving in the same direction. Like you have momentum moving forwards, and your body wants to stay with that same momentum. So when the car you're driving in moves to the side, your body wants to stay with that same inertia, that tendency to move in a straight line. It has that tendency, and so the car turning is disrupting that.
So is it a conservation of
No, it's not conservation of momentum. That wouldn't be a question you could have for that.